Can we have sea lunch?
We have B lunch.
Yeah.
Yes.
But we have C lunch?
Yes.
Yeah, it's similar to B.
Nice.
We have C lunch. She said C. Yes, she said it's
Why is this still what's showing?
Yes.
You did?
Right. It's a better game than yesterday. Okay, so
It's recording. So yeah, everyone's wearing clothes.
You're sure? I'm so cold. Just for this lesson.
I won't, trust me. Never again. Okay. So let's get started. I have okay.
Oh, what is this?
Ew!
I thought it was just a glove. It's like liquid.
Can I see it? Oh my gosh.
What is this?
It was so great.
Oh yeah, yeah. Can I take a picture like that?
No.
It was kind of dark.
So what is this?
Huh?
What is this?
What is that? That's a surgical glove filled with water.
Why you have that?
The sixth period I gave it to me. They said, here, in case things don't work out with Kelsey, here's another hand.
Is that like clean my kind of
No, that was a regular geometry class.
Yeah. Yeah, sure.
All right, so today, pretty simple, very computational based. It's a little weird, but just bear with me, and once we get about midway through the lesson, things will start to click. 31 slides, this is a big lesson. What's going on here? Of course. Do it. We cannot play hot potato.
Is it? You sure?
You sure?
Yeah. Well, you ready? Glove food. It's gonna pop if you drop it. Do you think it'll break if you drop it?
What, the glove?
Yeah.
No, the surgical glove is pretty thick is the word, I
You
think.
wanna try it out?
Let's play hot potato.
Nope.
Water. I thought it's just kind of like.
Okay, hopefully this is recorded.
Oh. Who's the real baseball player here? Older.
Oh my god.
So fried.
Why is this not working?
remember we had to simulate monkey cow. Inside a glove, and then you have to like bring it out. And I'm like, whoa. Yeah, exactly. Gotta warm it up.
Nobody else wants to. It's honestly, like something we need to have a discussion about.
Hey, Jack, that's you.
No, we'll have a lesson. Okay.
Okay. Ryan, have you ever fished out at the wall? You think the first right out. Pick up. Put it out. 100%. You wanna take some pictures to the bathroom? Oh. Whoa, now you can like draw. Whoa.
It's all the smartboard is. It's not as smart as people think it is.
But like, it's like now it's like an overhead projector, you know? You know what I'm saying? Like before you had like the plastic sheet, and then you write on the sheet with markers. You know what I'm saying?
Yeah.
That's cool.
Okay. So hopefully you're able to go. All right. Inner product. So sort of like dot product, but a little bit different. Okay. Oh my God, I'm gonna kill somebody. Okay. So we're familiar with dot product and if properties. We're gonna extend this idea, give this new thing an inner product, and it has a new symbol. Okay, brackets on the end, 20 brackets. A inner product is just a function that is defined by some operation on two vectors. So the inner product on a vector space V is a function that to each pair of vectors u and v is associated a real number, the inner product of u and v. This function is what defines various inner products. Okay. So the inner product of u and v is not necessarily the same as the inner product of a and b if that function is different. Okay. These four axioms must hold true in order for a function to be an inner product. I'm not going to spend the time to prove them. We could do that, but we will do this, and I'll show you that this is not an inner product. So, in order for this to be an inner product, those four axioms have to hold. However, the fourth axiom, the positivity axiom, UV is not guaranteed be greater than or equal to 0. In other words, this is not guaranteed to be greater than 0. It has to be greater than 0. That's for the fourth axiom. So, fourth axiom fails, therefore not an inner product. Okay. So you will have to show that a function is an inner product on a subspace, on a vector space. All right. Moving on. Okay. Vector space Rn with the standard inner product, the dot product. A dot product is an inner product, by the way. It's the standard inner product. As an inner product, or as an inner product space, and almost everything discussed for the dot product carries over to inner products. I can't touch that. So this actually looks a lot clearer. Lengths, distances, and orthogonality. So just as in Rn, we can define the length or the norm of a vector v to be the scalar. Okay. Equivalently, we can square both sides. However, this definition does not say that the inner product of VV is the sum of squares. Okay. Because V does not need to be in Rn. The distance between U and V is the scalar of U minus V. Okay. The unit vector is one whose length is 1. Vectors U and V are orthogonal if the inner product is 0. Some special inner products, weighted inner products. Weights are given to various entries in the sum, for the inner product in such a way that more importance is given to the more reliable measure. So, don't really deal with that much. But let's do a few examples here. So, we want to calculate the inner product of U and V based on this function. So I get 3 times U times V plus 5 times U times V. It is 3 times 1 times 5 plus 5 times negative 3 times 1. Excuse me, U1, V1, U2, V2. Got it. Okay. That is 0. Okay. The magnitude of U is the square root of the inner product of U and U. So that is the square root of 3 times 1 times 1 plus 5 times negative 3 times
U dot U.
What? This is U.
Yeah, dot U.
I'm not doing that.
So,
Wait, what?
why do you put 5 in there? It's U dot U.
Because the function that defines this is 3 times and then 5 plus 5 times. Where'd you think that 5 came from? Over here? Okay, this 5 is that 5. This 3 is that 3. This is the first coordinate of U, the first coordinate of U, or V, first coordinate of second order of use, second of heating. That's how this function is defined. We good now?
Yeah.
Okay. So I get square root of 3 plus 48, which is the square root of, that's not right, 45, which is the square root of 48.
Wait, so when those two lines on either side don't necessarily meet magnitude. Because if you just took like the magnitude u, you'd get like root 10. Maybe that's the length in that space. What it is, they're going to take in that
Yes.
space, new space. I think that's the magnitude in the new
The inner product
inner
space.
product space.
Okay. Okay. That's the only thing I can think of. Alright. So the length of V. Why is everybody leaving? Where's Agnes? It's not Michelle. Michelle's not here. Don't try to trick me. Okay, and then this is the distance from U to V, okay, which is square root of U minus V dot U minus U.
Unless you
Can the three of you see? Because remember, this isn't going to get on black. Okay.
But how are the people?
I'm recording right now.
Yeah, so I can.
Hi, Hayfield.
I'm recording video.
Go Hawks.
Yeah. How are they gonna see it?
They're going to watch the video.
Can we watch the video?
You can watch the video. I forgot.
Why are you eating?
Okay, polynomial inner products. Polynomial inner products. For P and Q, the inner products are defined as such. Now, the way the inner product of polynomials are defined is, notice that this is P of some value times Q of some value plus P of some value times Q of some value, so on and so forth. So it's the dot product of T from just say this. Okay, so for some values of T. I'm going to actually touch the board today. Okay, so given the polynomial P of T and Q of T, and we define the inner product to be the evaluation of the polynomials from -1, 0, and 1. Let's find these values. So the easiest thing to do is to first evaluate these polynomials in a table. Okay. So for t, I've got negative 1, 0, and 1. Okay, and let's see. P is negative 4, 0, 2. Q is 5, 3, 5. That's just from plugging in the values of t. And then the difference between these, negative 9, negative 3, negative 3. I'm going to need those later. Okay. So this is negative 4 times 5 plus 0 times 3 plus 2 times 5, which is negative 10. Okay, the magnitude of P defined as the square root of negative 4 squared plus 0 squared plus 2 squared, which in this case is 2 square roots of 5. Magnitude of Q is 5 squared plus 3 squared plus 5 squared, which is square root of 59. And this guy is 81 plus 9 plus 9, which is 3 square roots of 11. That's coming from negative 9 squared, negative 3 squared, negative 3 squared. Okay. Questions up to this point? Because now we're going to start talking about matrices. Okay. So inner products generate matrices. Okay. So U and V are some column vectors. And A is an invertible n by n matrix. Then the inner product of U and V is equal to some matrix A times U dot A times V. So that's how we define the inner product of matrices. So let's let U and V be these guys. And the product on R2 is generated by the matrix here. So let's find these. So UV will be A times U dot A times V. So we have 1, negative 1, 0, 2. 5, 2, dot 1, negative 1, 0, 2, 3, 1. Which comes out to be 3, 4, dot 2, 2, which gives me 14. The magnitude of U is just U dot U, the square root of U dot U.
We don't have to multiply by A.
No. Magnitude of V. Oops.
Yeah, a lot of local motives. Why does the next never turn versus side?
This would be, this is where I'm going to miss using the whiteboard. U minus V dot U minus V. Hey, Nas, can we save it for lunchtime? Can we save it for lunchtime? say it for lunch?
So rude.
Comedy act? Yes? Okay. Thank you. Okay. So I would first find u and v, excuse me, u minus v, which in both, which would be 2, 1. And then I would perform this action on those two. I know, I'm so sorry. I can't
Are they both
extend
the
it.
same back to 2, 1, 4, 1?
Yeah, they should be, because it's u minus v dot u minus v.
You're saying we do have to multiply those by A.
Yes,
Why didn't we have to multiply U and V by A?
because this is not, it's not the magnitude of the inner product. It's just the magnitude of the vector. This ends up being u minus, I'm not 100% sure. Just, I'm not sure. Now that I go back and look at it, it makes me want to actually multiply by it and assume that these notes from last year are wrong. I'll double check on that, but yeah. Sorry.
Okay.
What's your question, Brooke?
Do you do AB or AB is there?
For this year?
No, for B and C.
I think so. Going back and looking over the notes, I think that's what I would do. But I'll double check. It should be in your textbook for sure. I just haven't had a chance to look at the textbook for this section. All right. Okay. The calculus inner product. So, given two continuous functions, f and g over the interval a to b, we define the inner product of f and g as just the integral of the product of those functions. So we're back to being able to do a little bit of calculus, which is nice because I missed this. All right, so here we'll have the integral from 0 to 1 of f times g. Comes out to be 5t to the 4th minus 8t cubed plus 3 t squared dt, which gives 0. I'll assume that we can integrate that. The magnitude of g is this, which means I would be doing the integral from 0 to 1 of g times g, or g squared. And that will come out to be 1/105. But I want the square root of it, so that would be my answer. The mathematical
Rationalized function.
I don't have to do anything but breathe and die. Yeah, if you really wanted to, you could. You're at the point in your mathematics career where you get to make that judgment call. And your teacher is not going to get on your butt about not rationalizing. Only people that are going to continue to rationalize the denominators are the ones that really get bugged out about the fact that you're dividing by a irrational number. That's why that's why mathematicians like to rationalize the denominator, because division by an irrational number is rational. It doesn't make sense. So we like to change it to this, because it's easier to conceptualize. We're dividing an irrational number by irrational. You can imagine that division. I'm trying to call it out. Trying to inform. Okay. Graham Schmidt. Ooh, where'd he go? There he is. This guy.
One guy or two guys?
I'm not 100%. I'm gonna assume it's two guys. The existence of orthogonal bases for finite dimensional subspaces of the inner product space can be established by the branching process, just like we previously done. The orthogonal projection of a vector onto subspace W with an orthogonal basis can be constructed as well. So we're going to do very similar things, but just with inner products instead. And the projection does not depend on the choices of the orthogonal basis, and it has the properties described in the orthogonal decomposition theorem that we talked about. Thank you. Okay, so compute the orthogonal projection of Q onto the subspace spanned by P, for P and Q here. So these are the same guys that we had before. We're going to use the same values for T. Okay, so we're looking for the projection of Q. So we're looking for Q hat. We want to project Q onto P. So we'll have the inner product of Q P over P times P. So this, if you remember from a few slides ago, came out to be -10 over, let's see, this should come out to be 20. We could go through and do that, but not necessary.
Question.
What?
So whenever we do the inner product of polynomials, we're doing the -1, 0, 1 thing.
Just, that happens to be for these examples. We're using -1, 0, and 1 for these examples. We could change the space by choosing different values of T. It would just, I think all it would do is focus in on another area of the space. Does that make sense?
I assumed it was going to be like turning vectors, like.
You assumed it would be like turn it into what?
So like vectors, like.
Oh, turn the equations, these into vectors?
Yeah.
Like parametric?
Like P would be like 0, 3, -1. And Q like 3,
Oh.
2.
No. Sorry. Okay, times P, which is 3t minus t squared. So Q hat is negative 3 halves t plus 1 half t squared. And so projection of Q onto P. Okay. All right. So now we're going to look at the two most important inequalities in mathematics. Does anybody know what one of them is? It's a triangle inequality. And the other one is the Cauchy inequality. So, given vector v as an inner product space, given vector v in an inner product space v, and given a finite dimensional subspace W, we can apply the Pythagorean theorem to the orthogonal decomposition of v with respect to W and obtain this equation. Okay. Let me draw a picture. Excuse me. Yeah.
Drinking water.
Yeah. Like through my butt. Like.
You're like you doing this, you like the other way.
Do you know what all of those tricks have in common?
You're supposed to do something with your lungs.
They force you to focus on your breathing and your diaphragm. Because your hiccups are just your diaphragm isn't consistent with your natural rhythm of breathing. So your diaphragm tries to breathe, but you don't want to, and so it hiccups. So just by concentrating on your diaphragm and your breathing, you can get rid of the hiccups. No tricks. All right, so we have a space W here, okay, and we have a magnitude of vector V, right, and then that projection onto W, right, is this. And this is just the difference of V and that projection. So we're really just using the Pythagorean theorem and squaring the sum of these squares is equal to V. So that's where that's coming from. I wish I could write on the whiteboard all the time. Handwriting is so much better. Huh? I mean, I could. This isn't anything but a glorified whiteboard.
Can I go to the house?
Just always do it.
Yes, you may.
What was stopping you before?
Huh?
What was stopping you before?
The fact that this is really awkward. I don't have a whole lot of space in here. Okay. Moving on. We're almost done, guys. Almost done. I would love to finish before lunch. Okay. The Cauchy-Schwarz inequality. Cauchy-Schwarz inequality says that for all u and v in V, the magnitude of the absolute value of the inner product of u v is less than or equal to the product of the magnitudes of u and v. So if we start with this, okay, and divide both sides by this product, what does this look like?
Unit vector.
What does it look like?
Unit vector.
No.
Orthogonal projections, kind of.
Huh?
Orthogonal projections, kind of.
Sort of.
Give us a hint.
Has to do with two vectors.
Heads to cross.
Has to do with finding
Parallel cliff like this.
some relationship between these two vectors. It's from first semester.
What's the first letter?
C.
Cross.
Let's say that's cross product.
Cross product.
That's not
Central commercial.
If you have two vectors, what might be one relationship that you might want to know?
Corollary.
No.
Exactly.
What is the C come from?
Where's the C?
Cosine.
Oh,
This is
wow.
cosine. This is your cosine theta equals UV of UV. And what is the what's the range of cosine? Boom. So this shows that the cosine of the angle between two vectors can only range from -1 to 1. Just missed the coolest part of the entire year. I don't think so. Okay, so the cosine of the angle between two vectors is equal to cosine theta, blah, blah, blah. So the Cauchy-Schwarz inequality guarantees that this value, cosine theta, is between -1 and 1, no matter what the dimension of Rn. So we have a true geometric meaning in R2 and R3. Okay, our primary interest would be to determine the orthogonality of given vectors. So we want this to be 0. 0. Okay, when we define cosine theta as this equality, our theta is defined to be in the interval from 0 to pi. The Cauchy-Schwarz inequality is useful in many branches of mathematics, but the main use for it here is to prove another fundamental inequality, which is the, am I there yet? No. It's coming up. I'll do an example or two and then get into it. All right, green. Okay, let u be 7, -1 and v equal to 3, and I've got, this is the same. Bless you. This is the same function that defined the inner product in that first few examples. Find the cosine theta between u and v. Okay, so cosine theta is u v over u v. We've already calculated that, and it was 27. That's not right. Yes, it is. So theta equals the arc cosine of this. Theta equals 1.271. So when I ask for finding, no, sit down. Whoa, you just got here.
Yeah.
Pick it up. I forget. All right, what about the cosine, the angle between two polynomials? Okay. Notice that I should be defining I should be defining this every time on some or some values of t. Could be more, could be less, could be different. So again, these are the same as last time. Here's P, here's Q, -1, 0, 1, -4, 0, 2, 5, 3, 5. So cosine theta -10 over the square root of 20 times the square root of 59. 11. Close. Got carried away. So theta is the inverse cosine of -10 over this, which is 1.866. And of course, this is all in radians. All right. Questions up to this point? So, if you continue along the mathematics track in college, you will come across this inequality inevitably. As far as my professors were concerned, this is the most important inequality in mathematics. It hasn't been. And it is called the triangle inequality because it's really talking about sides of a triangle. U, V, excuse me, A, B, C, and that's that same old thing of B plus C has to be greater than A. That's where this comes from. Should be evident why this is true because if either one of these is negative, then this would be less. This is the reason that we have triangles. So you use the triangle inequality in a lot of the sort of grounding proofs in upper level calculus. So we can generalize the Pythagorean theorem to say this, okay? And what this helps me with here is that's only true when I have a right triangle. Therefore, I can use this to verify that I have orthogonality. So verify that the set of vectors is orthogonal with respect to the inner product, and then convert it to an orthonormal set by normalizing the vectors. It's already orthonormal, right? These are both unit vectors. Okay. Got it. Yay. Okay. So all I need to do is find the inner product. Since the inner product is 0 based on the generalization of the triangle inequality, I should have two vectors in one way. So that's just pretty much that. We have 2 more sections to do this year. And then we are done. I know. I wish we were done last week.
Do we have another unit test or is this fine?
There's a unit test. So I think what we had decided last class was, that next class I will teach the last two sections, and they're both from chapter 7. It's like 7.1, 7.2. And then Thursday, we have class for 2 hours. So we'll spend the first 30 minutes reviewing, and then we will take the test. I'm supposed to be emailing the attendants over there to see if I can let them stay until have them be back by 10 instead of 9:30, because we get out at 9:21, so that would give them 40 minutes to get back to me. They just might be they'll be late to their second class. Whatever. And I think their contract just means that if they're back by their contracted time, then they're excused. If they're back after their contracted time, it's just an unexcused tardy. Well, it's not like they're going to go to jail for true. All right, let's see.